This video is brought to you by Hackeramo Chalk. Use code TPSA 10% off to get a discount.
My name is Niall, and today I'll be walking through a tutorial on how to run your first program using Qiskit on a quantum computer. This is part of the lecture series offered by the TPSA as part of the Qiskit Fallfest 25. And alongside this video, we'll be sharing a link to Google Colab. Google Colab is just a simple online interface for running your code. And the first part of the system is to download all the necessary packages to the latest updated date so that we're all working off the same level. The next thing that we will require for this video is that you set up an IBM Cloud account. I would suggest that you pause the video and go to IBM Cloud onto their quantum platform and sign up for an account. As part of signing up for an account, you can create a free tier on their quantum platform to get 10 minutes a month of running your problems on a quantum computer. Once you create an account on the IBM, there'll be a page like this listed here, where you'll be able to create an account instance. All this is a centralized place to keep track of how much usage you're using on a quantum computer and how many jobs or tasks that you have sent to different quantum computers. Once you've created this instance, you'll be able to copy an API key and a CRM. These are both necessary to allow your code either on your local computer or in Google Colab to connect to IBM. Hopefully all this is set up and we can start working through this tutorial. You need to save your API and your CRM. Once these are saved, they'll be saved onto your environment, and then you'll be able to run each element of your Qiskit code on a quantum computer. We can begin now. The first thing we'll be doing today is creating a simple quantum circuit. Then we'll be preparing the circuit to be sent to a quantum computer before measuring and running the quantum circuit on a quantum computer. So the first thing we will look at is how to create a quantum circuit. Creating quantum circuits in Qiskit is very straightforward. First thing you'll do is use this object quantum circuit, this function, and list how many qubits you want in your circuit. This is analogous to how many wires or how many bits you want in a circuit in the classical world. In this case, we'll use 2 qubits. Let's see, they're listed here. The 0th qubit and the 1st qubit, 2 qubits. And then we'll apply a Hadamard gate and a controlled X gate. The Hadamard gate is it places a qubit, which starts in a position 0, a bit 0 as you can think of it, and it transforms it so that's in a superposition. So there's a 50% chance of measuring it in the 0 or a 50% chance of measuring it in the 1. And then what we can do is we can visualize these circuits. So we can draw these circuits so we can check what we written out in code is what we expect to perform. Once we've created a circuit, what we can do is we can measure our circuit. We can measure our circuit with these different objects, these Pauli operators as they're called. And all these mean is that we're measuring our qubit, which if you remember from the previous lecture, can be represented by a sphere, in different bases. And what we're doing is measuring the probability of it being fully in one of these bases, so in one of these directions. One direction could be fully up, fully to the side, fully to a different side, and these allow us to get a full idea of what our information is on a certain qubit. In this example, as I said before, we're using 2 qubits. We'll be able to measure both of these qubits in different bases. For this example, we'll be measuring it in these listed observable holes. And all they are is saying, I will measure it in the I basis, I'll measure it in the Z basis, in the order of the qubits. So it'll be I1 and Z I0 and Z1 if you're talking about Qiskit code labeling starting at 0, or just in general manner, the first qubit will be an I, the second qubit will be in Z. The next thing to talk about is optimizing our circuits and operators. What happens when we're running our quantum circuits on different quantum computers is that some quantum computers have some gates and some quantum computers have different gates. What we need to do is we need to use this thing called a transpiler. And what that does is it transforms our circuit from one backend, so backend being the type of quantum computer being used, to a different backend. This allows us to run our generalized quantum circuit on any of the available quantum computers. Not only does it do this, transferring gates from one backend to another, it also attempts to reduce the size of your circuit. In some instances, there's certain identities, as they're called, where a number of gates are in a row or in different scenarios can be reduced to more simplified amount of gates. This allows us to reduce what's called the depth, and all that is the amount of gates applied one after each other. The reason why we want to reduce these number of gates is that if we have the current quantum computers, if we apply too many gates, that takes a much longer time and errors begin to build up. In order to reduce those errors, we try and minimize the amount of gates we use. Using our connected IBM account, we can see what backends are available at a certain time and then select one of them. In certain instances, you can do as what I've done here, where we just list them and we select either of these backends, or you can use a function that's listed in the Qiskit documentation that selects the least busy quantum computer. For simple tasks, any quantum computer will do. Let's run our code and generate the circuit as expected. We'll list our observables. We will find what circuits are available. This might take a second because it has to connect to the backend. There we see the two quantum computers. And then, as I said before, we'll need to optimize towards our backend. From before, we had a slightly different circuit, if you remember. We had the Hadamard gate and a CNOT gate, as it's called. In this case, our circuit has been transferred into these different sets of gates. Some of these are rotations, and some of them are other gates that you'll learn as you study more quantum computing. This allows us to run it on the IBM Torino machine. I will just optimize it again to make sure it's set to the right gate. And once again, they're slightly different, but they'll be able to run on this quantum computer. Next, there's two things that are included in this primitives area. We have what is called an estimator, and we have what's called a sampler. These are both ways that we can try extract results from a quantum circuit. An estimator, what will it do is it'll try estimate the value as given by the name. But what it'll attempt to do is, given the different observables, as we've seen before, it'll try estimate the expected result. An estimator would say if you have a 0 and a 1, it'll take the average of them and it'll be 0.5, so estimate the result. Whereas with a sampler, what we'll do, it will measure a 1 and a measure a 0 and return it like that. These both have different cases where they're useful. In this case, we're going to use an estimator to estimate what observables will be returned by these circuits. This will create a job ID with the IBM Cloud. Because we are using one of their main backends, their real quantum computers, to generate a set of results based on that quantum computer. Once we collect these results, once they've been loaded in, well, that should take a second. In some instances, your job will be queued as it waits to run on a quantum computer. I'll briefly talk about fake devices. Currently, we're presumably sitting in a queue waiting to run on a quantum computer. Use what's called a fake provider. And this just allows you to run it on a local simulator before running on a real quantum computer. And now that our job is done, we'll continue on to our next section, analyzing the results. Once we've sent our circuit to a quantum computer, we can specify a number of shots. In the previous code blocks, we specified a number of shots. How many times you want to send the circuit through a quantum computer, or at the end of each one, it will measure it. Using these results, they'll be returned in what's called a PUB, and there's a variety of methods that you can use to extract these results and to do interesting different bits with these results. In this case, what we'll be doing is we'll be looking at the values of the observables that we originally were looking at and what results are returned with them. So in this case, we'll be looking both at standard deviations and their expectation values. So their values, and this is on the side, and which observables we use. In this case, when we look in the ZZ and the XX observables, so measuring the Z basis for both qubit 1 and qubit 2, the X basis for qubit 1 and qubit 2, we get a value of 1. And for all these other observables, we get almost 0. These little bumps are a result of noise or errors that come up based on the qubits in our system gaining some noise from the environment there. And that's why we do a large number of shots. What we'll do now is that we'll make a much bigger circuit. And this is how we're going to show the current generation of quantum computers and how large of a circuit you can run based on the number of qubits rather than depth. In this problem, we're going to create what's called a GHZ state. And it's similar to an extended Bell state where a lot of the qubits are entangled together. And the great thing about Qiskit is that we can use our standard Python to generate these quantum circuits without listing them out one by one for each state. This would become tedious if we're doing a 100 qubit gate circuit. We'll create a quantum function that will create Hadamard for a number of the qubits and then allow us to create that as a full Qiskit circuit. This is the exact same as before, but this time we have to do it for 100 qubits. We'll create a list of them and make sure they are the right length. And this time, it's even more important that we optimize for our backend, our quantum computer, to make sure that we aren't running an excessive amount of gates for the quantum computer we have in question. We will run a optimization to see if we can reduce the size of our circuit and make sure it runs on our backend. Once this is done, there will be a number of noise elements used so that we can reduce the amount of noise affecting our system. A lot of these noise protocols are highly complex, but are offered in a simple scenario to the user where they are able to enable or disable these noise reducing techniques. You can read up more on these noise reducing techniques on the Qiskit webpage. We will enable these techniques for reducing noise, and hopefully this will allow us to run our entire circuit on the quantum computer with reduced amounts of noise to get the results we want. And now we will submit our job and hopefully it will run quickly. What we can do while we're waiting is we can run the next block of code, and based on the job result being complete, so the job being complete, then it will return the result. In this case, we'll get a result from our quantum computer and generate the graph we want in this case. We'll be plotting the results between the Z0 and a Zi qubit. This is the expectation that both of these are in a 1 state. As we increase the number of i's, we're getting further and further away from an original I. And here that you can see the full formula. We start once we're in Z00, so measuring the Z basis for both the 0 qubit and the first qubit, we get almost a state of 1. And as we move along, these measurements become lower and lower. These observable values become almost 0. And that is all for this quick tutorial on how to run your first program on a quantum computer. In the next tutorial, we'll be showing you how this is useful. We haven't shown you how these algorithms that many people have heard about, or you may have heard about online, on how quantum computers can actually change how we do things in real life. All we've done today is measured observables on a quantum computer, but it is a good place to get started off to get comfortable with the process of running a quantum circuit. First, you have to create the circuit. Then you have to optimize and transpile it. Then you have to send it to your quantum computer. Then you have to wait for it and then get your results and process them. In another video, we'll be talking about QAOA. This is a type of optimization algorithm that in the near term offers potential speed ups on compared to other optimization techniques that we have, where you could solve many real world problems that are based on optimization, whether it's traffic routing or assigning people to schedules based on different constraints. And that should be in a video later in the lecture series. Thank you very much for listening, and I'll see you again soon.